Imagine watching like a critical alert just flash across your screen, behavior indicating ransomware activity. You have exactly 3 seconds to isolate the infected machine before it starts encrypting network drives.
Right. And when you look at the host name, it's just, a random string of characters like dstop 984F2 or something.
Yeah, and in that moment, you face an impossible choice. I mean, is that a generic guest kiosk in the lobby, or is it the primary routing server for the entire customer service call center?
Exactly. You isolate the kiosk, you're a hero. You isolate the call center server, well, the entire operation goes dark.
And you are having a very uncomfortable conversation with the chief operating officer.
Oh, absolutely.
So, welcome to the deep dive. If you are listening to this, you likely know the anxiety of managing a chaotic IT environment. I mean, whether you are dealing with 10 machines or like a sprawling enterprise fleet of 10,000 remote laptops, hoping for a pristine, perfectly labeled network is just a fantasy.
It really is.
Today, we are giving you the architectural blueprint to actually automate your security posture. We are mastering CrowdStrike Falcon's endpoint organization, specifically how to wield grouping tags and command line tools like Falcon CTL to bring order to the chaos.
And we are pulling from a heavy stack of technical sources today. We've synthesized official CrowdStrike Falcon documentation, the CCFA training guides, which is the CrowdStrike Certified Falcon Administrator, and several API integration manuals.
Right, so our mission today is simple. We want to move you away from manually clicking through endless lists of endpoints or, updating spreadsheets of IP addresses. We are going to explore how to dynamically tag, group, and automate security responses across your entire fleet.
Okay, let's unpack this, because before we can organize anything, before we can secure a device, we have to talk about how the platform actually identifies an asset.
Yeah.
And it's not by host name or IP address, right?
Wow, definitely not. Host names change all the time, and IP addresses constantly rotate as users travel or, jump between networks.
Right, of course. So visibility in Falcon relies on two immutable cryptographic identifiers. First is the customer ID, or CID.
Okay, so think of the CID like the company building address. When you install the sensor on a machine, the CID tells that sensor exactly which corporate headquarters it needs to report to.
Exactly. It links the local installation to your specific organizational tenant in the CrowdStrike cloud. Without that CID, the sensor is completely orphaned. I mean, it has no policies to pull down and nowhere to send its telemetry.
Wow, okay.
But once it checks in at that building address, the platform generates the second critical identifier, which is the agent ID, or AID. This is a 32-character hexadecimal string unique to that specific installed sensor.
Got it. So if the CID is the building address, the AID is like the unforgeable employee badge given at the front desk.
That's a great way to put it. It creates a permanent cryptographic bond. Even if a user renames their laptop or, say, connects from a hotel in another country, the AID remains the absolute source of truth for that host in the platform.
Right, but getting that badge onto the employee actually requires installing the sensor first. And looking through the documentation on how these sensors are deployed, there is a glaring architectural divide based on the operating system.
Yes, there really is.
If you are a Mac or Linux administrator, you deploy and configure the sensor using a streamlined command line tool called Falcon CTL. But if you are managing a Windows environment, you are required to use an entirely separate executable, windowsensor.exe. Why is Windows always the odd one out with its own exit installer, while Mac and Linux get to share the Falcon CTL tool?
Well, it comes down to how those underlying operating systems handle software installation at the kernel level. To provide real-time protection, the Falcon sensor needs to place hooks deep within the operating system.
Okay, so it's a fundamental OS difference.
Right. Windows relies on a heavily integrated registry and a traditional MSI installer framework. To safely place those early boot driver hooks in a Windows kernel, you require a packaged, compiled executable. Administrators deploy windowsensor.exe via the command line, passing parameters like install and quiet.
So it integrates with the Windows registry silently.
Exactly.
And the Mac and Linux architectures just bypass that entirely.
Pretty much. Mac and Linux utilize much more modular init systems, like launched on Mac OS or system on Linux. They don't have a centralized registry like Windows does.
Right, I see.
Because of that modularity, a lightweight command line daemon, Falcon CTL, can directly edit configuration files to set up the sensor without needing a bulky packaged installer.
But regardless of whether you are pushing an XO through SCCM for Windows or running Falcon CTL via GEM for Mac, the operational victory is basically the same, right?
Yep. The goal is unified. The sensor seamlessly connects to the Falcon cloud, pulls down policies, and starts protecting the machine without requiring a reboot.
That's huge.
What's really fascinating here is that deployment is also your first and best opportunity to organize your fleet. You don't just install the sensor and wait to sort it out later. You apply what are called sensor grouping tags during this initial command line installation.
Which brings us to the core focus today, the tagging architecture. Let's build a quick verbal comparison for the listener between the two primary methods of grouping tags. We have manual tagging versus automated grouping tags.
Okay, so manual tagging happens post-installation in the web console UI. An analyst physically searches for a machine, clicks on its profile, and types in a tag.
So very hands-on.
Yes.
Yes.
Very. Automated grouping tags, on the other hand, are programmatic. On Windows, you append the parameter grouping tags to your installation script.
And on Mac and Linux.
You pass those tags through the Falcon CTL command during the setup phase.
Okay, so comparing the two, manual tags require human interaction. They are applied after the machine is already running, and realistically, they are only good for temporary ad hoc classification.
Right.
Like if a security analyst is actively isolating a machine and tags it, investigating IR ticket 123.
Exactly. And conversely, automated tags via Falcon CTL or the Windows installer are applied at birth. They require zero human intervention once the deployment script is written.
Which makes them the only viable method for deploying at scale, I'd imagine.
Absolutely. The moment that machine checks into the cloud for the very first time, it arrives already labeled and categorized.
But there are technical limitations to these tags, right? Like, we can't just write a whole paragraph of text into a grouping tag.
No, you definitely can't. The API and the backend database have strict constraints to ensure the rule evaluation engine runs in milliseconds.
Makes sense. What kind of constraints?
First, there are character limits. A single grouping tag cannot exceed 256 characters.
Okay, 256 characters. Got it.
Second, there are formatting rules. When you apply a tag programmatically via Falcon CTL or the Windows command line, it must follow a specific syntax. It typically requires the prefix sensor grouping tags followed by your custom string.
Right. And what about volume? I mean, can I put 500 different tags on a single host just to cover all my bases?
Technically, yes. The platform supports multiple tags per host, and the limit per CID is massive, well into the thousands. But practically, you shouldn't.
Why is that?
Because inflating a host with hundreds of tags creates massive JSON payload bloat. Every time that host generates a telemetry event, it has to append all of those tags to the data packet.
Oh, wow. So it just bogs the system down?
Exactly. Keep it lean or you degrade the efficiency of your own rule evaluations.
Clean and organized. I like it. So let's talk about how these tags feed into host groups. The documentation outlines three types, right? Static, static BID, and dynamic.
That's right.
Let's tackle static groups first. I mean, if you've ever had to manually maintain a spreadsheet of 5,000 changing host names, you know why static groups are kind of an administrative nightmare.
Oh, a total nightmare.
You are manually adding desktop XYZ to a specific group. If the machine gets renamed, it just drops out of the group, like a pre-printed seating chart at a wedding where someone swaps name cards.
Which leaves that machine potentially stripped of its customized prevention policies.
Right, which is bad.
Very bad. Static BID groups solve the renaming issue by relying on that immutable 32-character agent ID we discussed earlier. Because the AID never changes, static BID groups are highly reliable for API workflows.
But they still require a script or an administrator to explicitly command the system to put this AID into that group.
Exactly. It's still a manual assignment at the end of the day.
Which brings us to the holy grail, dynamic groups. If a static group is a rigid seating chart, a dynamic group is the VIP list at a club where anyone wearing a specific wristband gets led into the VIP section automatically.
I love that analogy.
So there is no pre-printed list of names. You just create an assignment rule that looks for the wristband, which is our grouping tag. If a machine shows up wearing the neon green wristband, it automatically inherits all the policies of that group. Take the wristband off, it's out.
That analogy works perfectly, but with one critical technical distinction.
What's that?
The bouncer checking those wristbands isn't a human who can be bribed or distracted. It is a programmatic rule engine that evaluates data in milliseconds.
Wow. Okay.
When a host comes online, the rule engine checks the JSON payload of that host's check-in event, scans the tags array, and instantly drops it into the correct dynamic group.
But letting administrators just invent their own wristbands sounds like a recipe for a massive blast radius. Say an admin needs to group Windows servers. One admin scripts their deployment tool to apply the PAG windows. Another admin in a different branch uses Win servers. A third uses prod Win.
If we connect this to the bigger picture, Consistent naming conventions and dynamic tagging are what prevent a messy environment from becoming a security liability. Because if your dynamic grouping rule is only looking for the tag win servers, it completely ignores the machine's tagged windows or prod win.
And the blast radius of that is terrifying. Imagine a zero-day vulnerability drops. You push an automated patch script targeting your dynamic group for Windows servers because of inconsistent tagging. A third of your servers never receive the patch.
And 2 days later, they're compromised. That is the exact scenario the documentation aims to prevent by demanding a strict naming convention. The industry standard, heavily emphasized in the CCFA training, is the OS Purpose Environment Format, or OS Purpose ENV.
Okay, OS Purpose ENV. Let's run through some common examples of what that actually looks like across the different operating systems.
Sure. On a Windows server running web services, your tag applied during the X installation would be WinIceProd.
Got it. So this instantly tells the platform and any human analyst the OS is Windows, the purpose is Internet Information Services, and it is a production asset.
Precise.
What about full text?
If you are deploying via Falcon CTL via Jamf to the executive team, the tag is Mac VIP Corp.
Nice and clear. And Linux.
For a database server handling payment data, Falcon CTL applies the tag LinDBPCI.
So by adhering strictly to the OS Purpose ENV convention, your dynamic rules never miss an asset. Furthermore, during a live incident, an analyst looking at a randomized host name immediately understands the business context of the machine based purely on its tag.
Exactly. It removes all the guesswork.
Here's where it gets really interesting, though. We've used Falcon CTL and Windows installers to deploy our sensors. We've applied tags at birth. We've avoided payload bloat.
Right.
We've utilized the OS Purpose ENV convention to funnel hosts into dynamic groups without lifting a finger. But tags are not just organizational labels, right? Let's transition to the true power of tags. We are going to talk about Fusion Azure, security orchestration, automation, and response.
Oh, yes. This is where we transition from merely organizing the environment to actively defending it. Fusion Azure basically weaponizes those grouping tags. It operates on a very specific logic model.
Which is?
Trigger, condition, action.
Trigger, condition, action. Explain how the platform moves through those three phases and how our tags fit into the sequence.
A trigger is the catalyst. It could be a new critical severity detection, an identity threat, or an audit event.
Okay.
And actually, an audit event can trigger a workflow simply because a tag was added or removed from a host.
Oh, wait, really? Just changing a tag can trigger it?
Yep. The moment that trigger fires, Falcon generates a massive JSON event payload containing everything about the threat and the host, including its array of tags.
So the SOAR workflow wakes up.
Exactly. But before taking any action, it moves to the condition phase. It evaluates the JSON payload against the rules you've built.
Okay, let's go back to a real-world use case. Say Falcon detects an unknown executable trying to dump credentials. The trigger fires. High-severity detection.
Right.
Normally, the automatic action is brutal, network containment. You just sever the machine's connection to the network to stop the spread.
Yes, usually.
But what if that machine is Mac VIP Corp, the CEO's laptop, and they are in the middle of a massive investor call? Automatically isolating them based on a false positive is a fantastic way to lose your job.
Which is exactly why the condition phase acts as a circuit breaker. The workflow trigger fires, but the condition intercepts it. It scans the tags array in the JSON payload and asks, does this host possess the grouping tag Mac VIP Corp?
And because we set up our automated tags perfectly during deployment, the API sees the tag in milliseconds.
Right. And because the condition is met, the workflow branches. It bypasses the aggressive network containment action and triggers an alternative action.
Like what?
Request human input.
Request human input. How does that actually manifest for the security team?
The SOR platform pauses the containment. It immediately fires off a rich webhook, perhaps an automated message to a dedicated Slack channel or a Jira ticket, containing the full context of the detection.
Oh, that's smart.
And it presents the analyst with a button to either approve the containment, decline it because it's benign, or escalate.
Wow. So these tags aren't just filing cabinet labels, they're actually tripwires.
That's exactly what they are.
But how granular can we get with these conditions?
Right.
What if I want to pause for human input if it's a VIP, but only if the severity is medium? Because if the severity is critical, I don't care if it's the CEO, I want that machine contained instantly.
The SOR logic builder handles that easily using standard Boolean operators, so AND and OR logic. You combine a tag condition with a threat data condition.
Give me an example of what that looks like.
Your workflow logic would explicitly state, If tag contains VIP and D severity equals medium, then request human input. Arrow see if severity equals critical, then network contain regardless of tags.
That is incredible. That is the level of control that finally makes security teams comfortable turning on automation.
Yes, exactly, because you aren't just letting algorithms run wild. Combining tags with logical operators ensures that automation scales safely, preventing an analyst from accidentally isolating the CEO's laptop during a false positive. You are defining the exact blast radius of your automated responses based on the tags you apply to deployment.
And those actions extend far beyond just notifications or network containment, don't they?
Oh, definitely. You can use tags to autonomously execute real-time response or RTR scripts.
RTR scripts, like opening a remote shell and running custom cloud directly on the endpoint.
Yes. Think about a zero-day vulnerability dropping at 2:0 a.m. The immediate vendor mitigation is to kill a specific background process and delete a rogue registry key.
Okay.
You do not have time to manually remote into 200 vulnerable web servers.
No, you'd be breached before you got through the first 10.
Exactly. So instead, you trigger a WhereAre workflow. The condition targets your dynamic group using the tag WinIceProd.
Right.
The action automatically establishes an RTR session across that entire targeted fleet simultaneously.
All at once.
All at once.
Yeah.
It executes an RTR command, like kill to terminate the process, or get file to pull forensics, or put and run to drop a custom PowerShell mitigation script onto the disk and execute it.
Wow.
The entire fleet is patched in seconds, precisely because they were tagged correctly at birth.
So what does this all mean for you, the listener? It means that mastering this tag-to-automation pipeline is the ultimate shortcut to scaling your security operations. It respects your time by turning manual click work into automated logic.
Well said.
We walked through the deep mechanics of why Windows uses the Xporus installer to place kernel hooks, while Mac and Linux use the lightweight Falcon CTL daemon. We mapped out how utilizing those tools to apply grouping tags during deployment bypasses the nightmare of manual tagging.
And we established the absolute necessity of the OS Purpose ENV naming convention, recognizing that bad tags create a dangerous blast radius, where dynamic rules fail to cover vulnerable assets.
Right, and finally we saw how SOAR evaluates the JSON payloads of those tags in milliseconds, using them as logical tripwires to safely orchestrate automated containments and fleet-wide RTR scripts. It transforms your environment from a chaotic list of random host names into a self-managing, self-defending architecture.
It allows your security team to stop acting as human spreadsheets, constantly trying to figure out what a machine is during an incident. The context is already there. The logic handles the response. Your team is freed to actually hunt threats.
But we always want to leave you with something to ponder, something that pushes the boundaries of the documentation we've explored today. In reviewing the Falcon exposure management modules, there is a clear shift happening regarding asset classification.
Yes, there is. Up to this point, the entire architectural blueprint we've discussed relies on you, the human administrator, explicitly defining what an asset is. You are the one writing LinDB PCI into the deployment script.
But the platform is beginning to utilize machine learning, AI, to automatically analyze the behavior of an endpoint.
Right. The AI monitors what applications are launching, what internal network ports it communicates on, and what type of data it handles.
So it can look at an untagged machine and say, based on these patterns, this behaves exactly like a critical database server. I am going to dynamically suggest or apply that classification.
It represents a fundamental shift. The burden of context is moving from the administrator's deployment scripts to the platform's behavioral intelligence.
Which leaves us with this final thought. If grouping tags are the tripwires that trigger aggressive automated security actions, what happens to your security posture when the AI starts tagging and isolating risks based on patterns you haven't even noticed yet?
That is the bleeding edge of autonomous security.
Until next time, keep diving deep.